So hi everyone, this is like entire derivative review. I'm going to take around 10 problems and let's see if we can refresh the concepts. So the first couple of them are like specifically suited for AHL curriculum. And let me just start with the first one. The question is, if I have got y is x minus 2 the whole squared and 2x minus 1, uh, for what x values is your dy by dx 36? So first what I'm going to do is I'm going to find out the dy by dx. So dy by dx is 2 times x minus 2 raised to 1 and into derivative x minus 2, that's 1, and times 2x minus 1 as it is. So I'm applying product rule here, u and v. So the derivative of this is u dash v plus vu dash. So I'm doing that here. And next part is I'm going to keep it like this, x minus 2 the whole square. And then you got 2x minus 1 derivative is 2. So if you want to simplify this, what you could do is you could take, you can see x minus 2x minus 2 common. If I take 2x minus 2 common from entire stuff, we are left with 2x minus 1 here. And we are left with plus one of the x minus 2 as it is here. So we get 2 times x minus 2, and here we get is 3x minus 3. And now this part is basically the derivative, and it should be equals to 36. So if I equate this to 36, it becomes negative 4. So what we get eventually is x squared minus 3x minus 4 equals to 0. We factor this out, x minus 4 and x plus 1 and equals to 0. So x is 4 and x is negative 1. So these are the values of x where the derivative to this curve is actually going to be 36. So now let's go to the second question, which is about exponential derivative. They have given that f of 2 is equals to f dash 2. So what's the value being? So first the f of 2 is going to be e to the power 2a plus 2 plus 4. That's f of 2. And now let's find out f dash x first. So it's going to be e to the power ax plus 2 into derivative of ax plus 2, which is a plus 2x. So now I plug in x as for 2 here as well. So f dash 2 is going to be e to the power 2a plus 2 into a plus 4. And they are equal. These two are equal. So I'm going to equate them. So e to the power 2a plus 2 plus 4 is equal to a times e to the power 2a plus 2 plus 4. So this 4 and 4 gone. And if you bring it here, so it'll become e to the power 2a plus 2 minus a times e to the power 2a plus 2 equals to 0. E to the power 2a plus 2, comma 1 minus a 0. So this part is not going to be 0 because it's exponential function. So you get a as 1. So this is like the one of the recap on exponential derivative. Now let's go ahead to the third one, which is finding out the derivative of the logarithmic function. So here we have been given that find the derivative ln 1 minus x squared times root 3x plus 2. So you're going to just do the one thing is that apply the log property and you can just simplify it rather than doing quotient rule now out here. Okay, so this part is important. Minus ln x to the power x. So it's like product rule here. Ln AB is ln A plus ln B minus ln C because it's a denominator. Now I can do the derivative of this. So f dash x is going to be, just modify this root because if you do ln of root 3x plus 2, it becomes half ln 3x plus 2. So that's what exactly I've done here. And this x can be brought down. So ln x to the power x can be brought down and written as x ln x. So you're going to do the derivative here. So 1 over 1 minus x squared times negative 2x plus 1 half into 1 upon 3x plus 2, 1 upon 2 as it is, into derivative of 3x plus 2, which is 3. And we have to still do the derivative of minus, basically x ln x. So to do the derivative of that, product rule, so x times 1 over x plus ln x times 1. So what you get is final derivative is negative 2x over 1 minus x squared plus 6 plus 3 over 6x plus 4 and minus 1 plus ln x. So this is the exact derivative of the expression number 3. Now coming to the last part here, that is second part, which is y equals to sine x to the power of root x. Now once again here we got to apply a little bit of our logarithmic function. So y equals to sine x to the power of root x. If I go on to differentiate this, apply ln y is going to be root x, ln sine x, and now you do the derivative of this. So apply implicit differentiation both the side with respect to x, and let's see what we get. So this becomes ln y derivative is 1 over y times dy by dx, and this equals to the product rule out here. So root x times derivative x. So root x times derivative of ln sine x. Now derivative of ln sine x is 1 over sine x times cos x. That becomes 1 over sine x times cos x plus ln sine x times derivative of root x, which is, since we've done so many questions, now I can just remember that, writing it straight away in this form. So now dy by dx is going to be y times root x cot x, because cos x upon sine x is that, and ln sine x over 2 root x. And now you're going to multiply, put the actual value of y, which is sine x times sine x to the power root x, and root x cot x plus ln sine x over 2 root x. So that's how you kind of do the derivative of this part as well. So these are the few of the derivative skills that are related to techniques of differentiation. Now let's try to do some of the questions in more depth. So what you got to find out is the derivative of half arc sine x, and g of x is sine 2x. So when you're finding out the derivative of this, so f dash x for arc sine x is given data booklet, and it is root 1 minus x squared, 1 over root 1 minus x squared. And since there's a half here, it gets multiplied. So that's the derivative of that part. And now g of x is sine 2x. So g of x will be f dash, g dash means sine 2x. Derivative is cos 2x. So you can differentiate that out here. So cos 2x into 2. So cos 2x into 2. Because you remember that sine of x derivative is simply cos fx times f dash x. So these are the derivative of this part. And what you get is, now next part is, so this answer is 2 cos 2x. All you have to do is find out, hence show that the derivative of f dash of g of x times the value f dash of g of x times g dash x is equals to 1. And given that the domain is x between negative pi by 4 to pi by 4. So firstly, what we have been given is that if you see, this is nothing but the derivative of f of g of x. If I look backwards, when I find out the derivative of f of g of x is actually f dash of g of x times g dash x. That's the derivative of this. So now you've got to work backwards for such question. Now what I will do is, okay, so firstly I'll find out f of g of x function, and f of g of x is half arc sine 2x instead of arc sine x, now arc sine of 2x. And this becomes basically nothing but x. Now, assuming that, like, now just coming to this minus pi by 4 to pi by 4. Now, since you know that arc sine x domain is x between negative 1 to 1, basically just you're talking about this. So any values that is between minus 1 to 1, which is like the range of the function, range of sine 2x should be minus 1 to 1 basically. But that is going to act like x value for f of g of x. So If you simply look at the sin x graph, where it is between -1 to 1, so this is minus pi by 2 to pi by 2. But since this is sin x graph, sin to x graph will be minus pi by 4 to pi by 4. This which will make the function 1 to 1. So this range gives us the value, which is like going to fit in -1 to 1. So when you're finding out the this particular domain, obviously that would be same as the domain of the original function that we choose. Hence, this is minus pi by 4 to pi by 4. You just should like always highlight this while you're doing this particular kind of question. So here we got to now the fifth problem, which is find out the derivative of x cubed plus y squared equals to 7, the second derivative. Okay, so what you do is, like, obviously, just remember that when you're differentiating x to the power n with respect to x, it is nx to the power n minus 1. Like, as you're differentiating y to the power n with respect to x, it will be ny to the power n minus 1 times dy by dx. So now let's start with this. So first, if you apply derivative both sides, so you get dy by dx is of basically derivative both the sides. So x cubed derivative is going to be 3x squared plus y squared derivative will be 2y times dy by dx equals to 0. Now from here, what I get is dy by dx is going to be negative 3x squared over 2y. Now, if I differentiate this, I can get the answer. But what I would prefer to do is, I would prefer to differentiate this expression itself. So when you're finding out the derivative here now, you could just differentiate the expression which you got in this step. So 3x squared plus 2y dy by dx equals to 0. So 3x squared derivative is 6x. And you're going to apply product rule here. So 2 times, now y derivative is dy by dx, and there is already a dy by dx here, and plus, then you do 2 times 2y times derivative dy by dx, which is d square y by dx squared equals to 0. So here what we get is 6x plus 2 times dy by dx the whole square, which is this. So 2 times negative 3x squared over 2y the whole square plus 2y d squared y by dx squared equals to 0. And then you solve for d squared y by dx squared. So when I do that, I'll get d squared y by dx squared equals to negative 6x, and this will become 9 to the 18. 18 x to the power 4. So minus 18 x to the power 4 over 4y squared. So over 4y squared upon 2y. And of course, if you simplify this, this is going to be, this you can simplify as 2y squared, and here will become negative 9. So if you take the LCM of this, will become negative 12, negative 12 x y squared minus 9x to the power 4 over this is going to be 4 y cubed. So that's going to be the second order derivative for this particular question. Also, you could have done an alternative approach also here. You could have taken an alternative approach after this step itself. So that's one way that we did. Now I'm just showing you the other way where you apply actually the quotient rule to get the second order derivative. So what you do is you do the quotient rule here. So left hand side is you're going to get d squared y by dx squared equals to here become 4y squared and 2y into derivative of this is nothing but negative 6x plus, minus negative 3x squared as it is into derivative of 2y, which is 2 times dy by dx. This is from previous part, and this is now going to become negative 12xy plus 3x squared into 3x squared times 2 is 6 into dy by dx. Now dy by dx we know is this negative 3x squared upon 2y and divided by 4y squared. So this 2 and 3 here, and you get is negative 12xy. If you take LCM, it becomes negative 12xy squared and you got 3 times -3 is -9. X squared times x squared is x to the power 4 upon 2y upon y in the denominator. And if you divide by 4y squared, it becomes 4y cubed. So you can see that both expressions are actually coming this well with the two different methods. So 2 to the power x plus 2 to the power y is 2. So 2 to the power x derivative is 2 to the power x. Just wanted to write on this formula. A to the power x derivative is a to the power x ln a. So 2 to the power x ln 2 plus 2 to the power y derivative to 2 to the power y into ln 2 into derivative of y, which is dy by dx, is equals to 0. Now after this, what we do is we are going to make the dy by dx the subject of the formula. So dy by dx is negative 2 to the power x ln 2 over 2 to the power y ln 2, which is negative 2 to the power x over 2 to the power y. Hey, here it's much more easier to apply straight away quotient rule. So this is going to be 2 to the power y the whole square. It will be 2 to the power y into the derivative of -2x, which is going to be -2 to the power x times ln 2. And I'm just going to write down here, continued step is minus uh, -2 to the power x as it is into derivative of 2 to the power y, which is once again it will be 2 to the power y ln 2 into dy by dx. So now after this, what you're going to do is substitute for dy by dx. So what we got so far, -2 to the power x, 2 to the power y ln 2, and minus become plus 2 to the power x times 2 to the power y ln 2, and in place of dy by dx, I'm going to put this minus 2 to the power x over 2 to the power y as a multiplier. So this cancels with this, and over 2 to the power 2y. So what you get is -2 to the power x, 2 to the power y ln 2, and plus, it will become minus again. So it will become 2 to the power x into 2 to the power x ln 2 upon 2 to the power 2y. So that's the derivative of this part. And what you could have done was, you could have done the derivative once again here in this step, and you could have still got the same answer. Just double check if there are any calculation errors. So an alternate approach is also like doing the same question after this step, where you can just straight away, you can take ln 2 common, and you get 2 to the power x plus 2 to the power y dy by dx equals to, let's say, 0 over ln 2, because I take common and divide, so that becomes 0 itself. So what we get is, after this step, you apply the derivative here itself. So you get 2 to the power x ln 2 plus 2 to the power y ln 2 times dy by dx times dy by dx as it is. So this is the derivative of this part, and times dy by dx. So I'm now applying product rule here, and 2 to the power y dy by dx becomes d square by dx squared. So I did u dash v. So u dash is all of this times v plus v, which is, uv dash. So uv dash is equals to 0. Now if you solve for d squared by dx squared, you get 2 to the power x ln 2. This part will become dy by dx the whole square. So this is -2 to the power x ln 2 minus 2 to the power y ln 2 dy by dx the whole square over 2 to the power y. So this becomes basically -2 to the power x ln 2 minus 2 to the power y ln 2 into the derivative that you see here, basically dy by dx the whole square. If you replace with -2 to the power x over 2 to the power y the whole square upon 2 to the power y. Now what you do is -2 to the power x ln 2 minus 2 to the power y. What we get is -2 to the power y here, ln 2, ln 2 here, and then this is -2 to the power 2x will become, this will become 2 to the power of, if you have dy by dx whole square, so it is 2 to the power x upon, into 2 to the power x, you can say, upon 2 to the power y times 2 to the power y, because squares, if you strike out one of this, upon 2 to the power y. And if you take LCM of this, that becomes negative 2 to the power x, 2 to the power y, basically ln2 minus 2 to the power x, 2 to the power x, and times ln2 over 2 to the power y times 2 to the power y, which is 2 to the power 2y. Because there is 2y here, if you divide it, it will become overall denominator is 2 to the power 2y. So that's how you do the derivative. This question I've shown two alternate approaches so that you can be confident of doing whichever way you want. So I'm not just going to do question number 6, which is find out the intersection of these two curves, which is so root 3x plus 1. I equated root 5x minus x squared. And if I equate them for intersection, so 3x plus 1 equals to 5x minus x squared. Bringing everything on side, so you get x squared plus 2x plus 1, x squared minus 2x, actually, if you bring it here, and I bring it here, plus 1 equals to 0. So if you factor it out, x minus 1 is 0. So you get is x is 1. Once you got x is 1, then our next step is show that the tangent to the curve. So there's only one point where it is meeting. So when x is 1, y is basically 2, root 4. So y is root 4. If you can plug in anywhere, you'll get the same answer, which is nothing but 2. So the coordinate of intersection is 1, 2. Now show that the tangent to the curve have the same gradient and intersection point. So what you do is you find out the derivative. So find the derivative of both the curves. So if I find out the derivative of this, it will be 1 over 2 root 3x plus 1 times 3. And the derivative of second is y equals to 1 over 2 root 5x minus x squared times y minus 2x. So that's the derivative of this part. So you're going to plug in x as 1 out here. So that's going to be 3 over 2 times 2, which is 3 over 4. Similarly, plug in x as 2 here, which is going to be dy by dx. This is, apologies, this is dy by dx. And you plug in x as 2 here, so it becomes 1. So what we get is this is dy by dx is going to be 1 over 2 times, sorry, this you plug in x as 1 here. So 5 minus 2 is 3, and 2 times, once again, you plug in x as 1 here. So it'll be root of 4, which is going to be 3 over 4. So you can see both the tangents are the same. They pass through the same point, and then you got to find the equation of common tangent. So you got now y equals to mx plus c, so 3/4 x plus c. Now you plug in x as 1 and y as 2. So you get 2 is 3/4 plus c. So c is going to be 2 minus 3/4, which is 8 minus 3, which is 2 over 4, which is 1 half. So 2 minus 3/4, which is this is, if I take, this is 8 minus 3, sorry, this is 8 minus 3, which is 5 over 4. So 5 over 4 is the c value. So your final equation that you get is y equals to 3/4 x plus 5 over 4. And that's how you write the equation of tangent. So let's go ahead to the next question now. Also, you can see the graphical evidence as well. So you got the two functions here, and so you can find the derivative as well. So now when you look at the verification, there are two curves. You can see that they're meeting at this point, and if you look at this as the tangent that we got, which is perfect tangent to both of them. So they have a common tangent, and this is a graphical evidence. Let's go to the next question. Now we got the next question, which is basically to find out the coordinates and nature of stationary points. So what you're going to do is you're going to find out the dy by dx first. So the first curve will be x times e to the power negative x times -1, because that's the derivative of this, plus e to the power negative x times 1. So I applied product rule, u and v. So it became u v dash plus v u dash. And then you're gonna take e to the power negative x common, negative x plus 1 equal to 0. So we got this as the derivative here. Now you can equate this to 0 and you're going to solve for x. So e to the power negative x can't derivative 0. So x is basically 1. Now once you got x is 1, you got to verify what kind of what kind of function is that. So either you can do the derivative sign diagram about, I mean, you can do the double derivative or you can do the single derivative sign diagram. So I will do this question using single derivative sign diagram about 1. Let's say if I pick up a value which is maybe 2. If I plug in x is 2 here, it'll be negative 2 plus 1, which is negative, and this is always positive. So it'll be negative here. And if I pick up, let's say, maybe 0.5 here, so if I take x as 0.5, it will be positive. So this entire expression is positive. This function changes sign from positive to negative, hence it's like a maxima. Now, to find the exact y coordinate, you plug in x as 1 here, so you'll get y as 1 over e. That's the exact y value. So this is how you do the first part. Now let's go to the second one. So in the second question, what we have is we have been given function is y is x minus 3 or x squared minus 5. E to the derivative of this x squared minus 5 to the whole squared using quotient rule. X squared minus 5 times 1 minus x minus 3 into 2x. So when you do the expansion of this, you get x squared minus 5 minus 2x squared, and this minus become plus, so it become plus 3 to the 6, so 6x over x squared minus 5 the whole squared equals to 0. So you get negative x squared plus 6x minus 5 is 0 if you equate to 0. So you get x squared minus 6x plus 5 is 0. So you get x is 1 or x is 5. So these are the two coordinates we got. Now, I really don't know whether it's maxima or minima. So you're going to draw the sign diagram about 1 and 5. Okay, so draw the sign diagram about 1 and 5. Of course, this is always positive. So this is, I mean, I'm not considering that. Of course, that answer will be like there's a vertical asymptote for the derivative, which is at root of 5 and minus root 5 as well. So when you're drawing the sign diagram of the double derivative, here you can see the denominator is always positive. Okay, so only thing is that you're going to check at 1 if I take, let's say, before negative 1, before 1 if I take, let's say, 0. If I take 0, this is this entire thing is 0 and the expression is negative. So this side will be negative, here will be positive. So that's going to be a minima at 1. And we'll just check that with the technology as well. So let's see what are we getting through the calculator. So the expression is x minus 3 over x squared minus 5. So I'm just going to plot them on Desmos. So x squared minus 3 over, so the expression is y equals to x minus 3 over x squared minus 5. So we can see that we got the x coordinate as 1 and the second x coordinate is we got is 5. So we got that from here our work. You can see from the previous part what we had got was definitely we got at x equals to 1 we had got the minimum. So at x equals to 1 here it was negative and positive, so it was minimum. And if you look at your draw sign diagram around 5, now you'll see that this is changing from positive to negative. And so that's a single derivative sign diagram. Hence, that's a maxima. So you can find out the exact coordinate by plugging in the these x coordinates here. So it'll be 1 comma 1 minus 3 or 1 minus 5, which is negative 2 comma negative 4, which is half. So it is at 1 comma half. There is a local minima. And if you plug in x is 5 here, so 5 minus 3 upon 25 minus 5, which is 2 over 20, which is 1 over 10. So that's your local maximum. So 5 comma 1 over 10 is your local maximum. So that's how you do the problems for the part 7b. Now let's go to the Question 8. So for the part A, what we're given is that you have to find out where the curve is concave up or concave down. Since you know that the double derivative represents concavity. So if d squared y by dx squared is positive, it's concave up. If it's negative, it's concave down. So what we do is I found out the derivative using quotient rule. So v squared vu dash, so derivative x squared minus 5 is 2x minus uv dash, which is x squared minus 5 times 1. You are going to then open the brackets, so 2x squared plus 4x minus x squared plus 5. So one of the x squared get cancelled, so you get x squared plus 4x plus 5 or x plus 2 the whole square. Now you apply the quotient rule once again to get the second derivative. So x squared, x plus 2 the whole square is this. vu dash, so the derivative of this is this, minus uv dash. So derivative x squared, x plus 2 the whole square is 2 times x plus 2. After this, what I did is I took x plus 2 common, and so one of the x plus 2 is gone from here. So you're just left with these two, which is here, and then minus 2 times this. And so one of this x plus 2 get cancelled, and you get the answer as x plus 2 the whole cube here. And if you open up the numerator, which is 2x plus 4 times x plus 2, which is 2x squared plus 4x plus 8 minus 2x squared minus 8x minus 10. Open up the brackets, so you cancel out this and this get cancelled. 8x and 8x get cancelled. 8 minus 10 is negative 2, or x plus 2 the whole cube. You draw the sign diagram. So at x equals to negative 2, there is a vertical asymptote for the double derivative curve. And if you take any value before, let's say after this, let's say at x0, it is going to be a negative answer. And this side is positive. So this side, the curve is concave down, and this side, the curve is concave up. So that's how you do the concave up is basically x more than x less than negative 2, and concave down will be for x more than negative 2. So that's how you do this kind of question. Now let's do the next one, which is y equals to log x to the base 2 plus x squared over 2. So this is going to be 1 over x times ln 2. Log derivatives, as you know, that's 1 over x ln 2 plus 2x over 2. This get cancelled, that's your dy by dx. Now what we get is your dy by dx is x to the power negative 1 over ln 2 plus x. So when you do it, and if I pick up a value, like for example, any x value, which is like bigger numbers, obviously minus 1 will be upon that will be positive. So here it is positive. Don't take any negative values. These are crossed out, and here will be negative. This side the curve is concave down, and then after this concave up. So this is like, it seems like a general observation for this. Now here is the last question. Basically, here the last question in the derivative skills. For what values of x is the curve increasing? Now remember that this has been given as a derivative curve. So wherever the slope is positive, positive means wherever the derivative is above x-axis means positive. So for slope for x less than x1, x less than or equals to x1, it is increasing. Now you have to find out where the curve is concave down. So concave down is where your double derivative is negative. A double derivative is negative. So where your double derivative is negative, basically, you can see that here it is negative until this point, and then after this it is negative here to here. So it's concave down for x less than or equals to x2 or x more than or equals to x3. So that's concave down because your double derivative both are negative here. After this, what we have to do is we have to find out, since given that the curve passes through origin, write down give the possible sketch of a f of x. So now, since you can see clearly that this is a possible maximum point because slope changes from positive to negative, and here slope is remaining negative and negative. So in this case, basically, this is a stationary point of inflection, and after this, what we do is we are going to find out the general shape of the curve. So here it is at x1 there is a maximum, So at x1, there is a maximum, let's say approximately like this. It passes through origin, I show like this. Then until here, until x2, you can see the curve is concave down, and after this, it becomes concave up. And so this is like a non-stationary point of inflection. And after this, what we do is it becomes concave up because the double derivative is positive after this step. So here it is concave down, after this concave up. And then there is a stationary point of inflection at x3. And so it's like decreasing until here. It's concave down, you can see. And then after this, still decreasing. But here there's a flat point at x3. And this is how your approximate function will look like. Coming back to the last part, which is sketch the double derivative curve. So double derivative is here, you'll have two roots. This side slope is negative, so negative, and then positive in between, and then again negative. So yeah, so you could see that the curve should be concave up only in these two intervals. So like whatever that part of the graph which we had got, like something like this, that was the only part was concave up, and after this was concave down. So that's how we had got this curve as the part B. Since you know that this is a variable x, I could take this as, let's say, y, this is x, and this is theta. So obviously you know that tan theta is nothing but y over x. And now what we do is basically we apply the related rates here. So tan theta is nothing but, if I do derivative, this is sec squared theta d theta by dt equals to, now you do here will become x squared as it is, x times derivative y, which is dy by dt, minus y times derivative of x with respect to t, which is dx by dt. So now at an instance when it is 1 meter, 1 minute, now since after 60 seconds, like from the beginning position, now after 60 seconds, this person will be basically would have fallen down by, this will be approximately 50 times 60 seconds, because this is in seconds, so 3,000 meters would have fallen down, so it will be somewhere here. And also the car would have approached by, let's say, 12 meters per second. So 12 times 60, which is 720 here. This is 720, it would have traveled. So the possible angle that now will be at this stage, you will have is, so this is, theta is going to be 4,000 minus 3,000 upon 1500 minus 720. That's going to be new tan theta. That's new tan theta here. So you get theta value. So tan theta, once you get, you can find sec square theta. Once you got sec square theta, you have to calculate this thing. And you already got x value, you got dy by dt. This is dy by dt minus y times dx by dt. So you just got to plug in this value. So if tan theta is, let's say, coming, this is 1000 or 1500 minus 720 is basically, so which is going to simplify to 100 over 78. And then you plug in that, I mean, sec square theta can be replaced with 1 plus tan square theta. You can plug that value here. You know this, you don't know this, you know this, you know this, you know this, you know this, and you know this. You can find out everything that is missing out here. So this is how I hope this is like complete revision for your derivative unit. I hope this is helpful.